Okay, so let's take a look at theorem 12, which is called variation of parameters. So it says if y1 and y2 are two linearly independent solutions of this differential equation equal to 0, then the general solution of the differential equation equal to f now is given by y equals c1, y1, c2, y2, this is the homogeneous part, plus u1, y1 plus u2, y2, this would be the yp part. And they're claiming that the coefficient u1 is given by integral of negative y2f divided by w, where w here is the Wronskian, and u2 is the integral of y1f divided by w. So we need to prove this. Okay, so let's start. Okay, so we're going to assume that y1 and y2 are two linearly independent solutions of the homogeneous differential equation up here equal to 0. And then we need to find conditions on u1 and u2 so that yp defined to be this. So u1 times y1 plus u2 times y2 is a solution of the non-homogeneous guy, so equal to f here. Okay, so I'm out of space here. Let me erase a few things and we'll keep going. Okay, so we have our yp, we're assuming looks like this, and taking derivative to find yp prime then, so you'd have to use product rule on this one, so it'll be derivative of first function e1 prime times y1 plus u1 times y1 prime, then using product rule on this one, it's over here. Now let's do yp double prime next. Okay, so yp double prime then, so it's going to be a long thing. It'll be applying the product rule to this guy. So it'll be y1 double prime times, sorry, u1 double prime times y1 plus y1 prime times u1 prime, sorry, times y1 prime, which I have here. That's the product rule for that one. And then the product rule for this one is these two. Product rule for this one is these two. And the product rule for this one is these two, as you can check. Okay, so now let's plug into the non-homogeneous equation. I meant differential equation. So I'm going to put the f on this side. So we're going to put our yp double prime to this long thing, place the yp double prime here, and place the yp prime. I'm going to put this, and then place the yp, put this. So doing that here, we get then, so making those substitutions, we get. Okay, so I made the substitutions for my yp double prime, this long thing here, and I actually noticed here they're both the same. I can combine them and be two of them here, and they're both the same, two of them here. So I just made a substitution for yp double prime, yp prime, and yp. So my yp is here, just up there. My yp prime is right there, which is here, and this up here is my yp double prime, which is this whole thing up here. Okay, now I'm going to rewrite it, so I can rewrite it as the following. Okay, so here's how I rewrote it. So I've underlined all these guys here, all the ones that have, this has u1, y1 double prime. This has, down here this has u1, y1 prime with a p in front of it. And this has u1, y1. So I'm going to pull the u1 out of these three things. Then I have, pulling u1 out of this one, I'd have a y1 double prime, which I have here. Pulling a u1 out of this one, I'll have a y1 prime and a p, which I have here. And pulling a u1 out of this, I'll have a q y1 here, which I have there. Then I did something similar with the u2, so you got a u2 here, a u2, and a u2. So factoring the u2 out of this one, there's a y2 double prime left here. Factoring out of this one, there is a y2 prime and a p. And factoring out this one, we'll have a q and a y2. And now by our assumption, we're assuming that the y1 and y2 are solutions of the homogeneous differential equation. So that means that, in particular, that this guy here and this are both 0. So let me write that. Okay, so again, this guy and this guy are 0 because we're assuming that y1 and y2 are solutions of the homogeneous differential equation, which means that this will be 0, this will be 0. Okay, so I'm out of space. Let me erase a few things and we'll keep going. Okay, so hence we have our f equals this then. Okay, we're going to make another observation now. So the observation is as follows. So the observation is if we take the derivative of u1 prime times y1 plus u2 prime, y2 is a product rule. So product rule on this one, these first two, product rule on this one, these last two. We get this. And notice we have that up here almost, because we have this guy, which is right there. We have this one, which is right there. And we have this guy, which is right there. And this one, which is right here. But we have a 2 in front of this. But we can rewrite this now. So rewriting, we can write it as follows. So making the substitution then for this up here. So this is identical to this up here, except we got a 2 in front of this one. So it'll be one factor of this left. So I have it here. And the rest of the stuff you can replace with this derivative. And then notice that this guy and this are the same. So they're both the same here. And our objective is now to solve for u1 and u2 and show that they equal what the theorem says. So in order to do that, we have to try and solve this now for u1 and u2. And it seems fairly complicated. But we can make an assumption here. Let's assume that this is 0. If that was 0, it would imply that that's 0 also. And then we just have f equals this, and we can then solve that guy. So let's make that assumption. Okay, so supposing, let's assume that this is 0. That's going to imply that the derivative of 0 is still 0, so this would be 0, this would be 0. And then this guy here then would have to equal f, so we'd have this implies this. So we'd have then a system to solve. Let me write our system that we need to solve now. So here's a system we have to solve. I'm switching the y1 and u1 prime around and the y2 prime and u2 prime and y2 around, and same over here. The reason is because I'm going to think of the u1 prime and u2 prime as the variables, and the y and y2 and the y1 prime, y2 prime as like the coefficients if you want. So we want to solve the system for u1 prime and u2 prime. So let's use elimination, say, to solve for u1 prime first. Okay, so to eliminate u1 prime, we're going to go y1 prime times equation 1. So I'd make a y1 prime here, then minus y1 times equation 2. That would be a y1 prime minus here, and they cancel. So I'm out of space here, so let me erase a few things and we'll keep going. Okay, so here's our system, and here's what we're doing. We're going to go y1 prime times equation 1. So y1 prime times equation 1 will be y1 prime times y1 u1 prime, y1 times y2 u2 prime, y1 prime times 0, which is 0, then minus y1 times equation 2, so it'll be y1 times y1 prime minus u1 prime, then minus u1 y2 prime u2 prime equals then y1 times f. So when you add these equations here, these two will drop off. And then combining these, we get then. Okay, so combine these, they both have a u2 prime. So I pull it on this side, and it'll be y1 prime y2 minus y1 y2 prime. And notice actually this right here is the Wronskian. So this guy's a Wronskian. We can then solve for u2 prime by dividing by the Wronskian. And then we can integrate both sides to find u2. So integrating both sides, we get then. So integrating both sides, we get then u2 equals this. And that's what we're trying to show for that one. And to show y1 equals the other part, we can just use the other part of the theorem, we can use this system up here and just eliminate the y2 prime and let you leave that as an exercise. So just right here. So in a similar way, I just actually has noticed something here. I'm off by a minus sign. This is actually not the Wronskian, it's the minus Wronskian here, which then would make this take away that minus sign, take away that, and in a similar way, we can show then that u1 would equal then the integral of negative y2f over w dx. So you just eliminate the y2 prime and do a similar argument, and you get this. Okay. So that's what we're trying to show. We found our u2 is this, and our u1, that's what the theorem was saying it should be. So we're done, so let's leave it there.